Welcome to tutorial 11, and in tutorial 11 we're going to be using oscilloscopes to measure the output of a 555 relaxation oscillator. This is the first time we will have used oscilloscopes. The relaxation oscillator is the same circuit we used in the last tutorial, except for this time these values are a lot smaller, the value of the capacitor and the resistor, which should give you an indication of what's going to be happening in the circuit. I just want to spend a minute explaining about the value of the components, especially these capacitors, because the 1 microfarad capacitor is an electrolytic one, but the 0.1 microfarad is not. And I just want to explain the numbering system to do with that. So a 0.1 microfarad capacitor, which when we enter it into our calculator, we enter 0.1 times 10 to the minus 6. If we move that decimal place back 6 places, 4, 5, 6, 0.00000001 of a farad, which is a very small amount. But likewise, 0.1, which is generally a fraction of a number, if we move the decimal place forward 3 places, we end up with 100. And in this case, it's 100 times 10 to the minus 9. In other words, this is 100 nanofarads. If we were to move that forward 3 more places and we add on another 3 zeros, that would be the same as writing picofarads, because picofarads is times 10 to the minus 12. Now, if we look at this in a slightly different way, as we would a resistor color code, the first digit is a 1. The second digit is a 0. And then we have 1, 2, 3, 4 more zeros. So 104 is a 100,000 picofarad capacitor, which is the same as a 100 nanofarad capacitor, which is the same as a 0.1 microfarad capacitor. And it's important that you understand all those are the same. However, we don't need to do that every time, because you can always refer to a chart, a capacitance table here. So here we go. If we look at microfarads, here is our 0.1 microfarad. We also know that it's equivalent to 100 nanofarads, 100,000 picofarads, and it should have written on it the code 104. And whilst you won't be able to see that, in front of me down here, that little blue-headed capacitor is a 104 capacitor. Okay, let's move on with the experiment. So I built my circuit using the values 2.2 k ohms and a 1 microfarad capacitor. I'm going to turn the circuit on and the LED should flash. Now, that LED is actually flashing at the moment. The problem is it is flashing too quickly for you to see. It's flashing many times a second. We certainly wouldn't be able to measure that with a stopwatch as in the previous tutorial. So we need to now use this piece of equipment here called an oscilloscope. Now, the oscilloscope requires quite a lot of setting up, so I'm going to turn my oscilloscope on and you will see a line appear somewhere on the screen. The first thing that we do, and we're going to be using just channel 1 in this. Your teacher can always help you set these up, but we're going to be using channel 1. I'm going to put it onto ground. And what I need to do, I need to position on my channel that line exactly in the middle. That will make our measurements a lot easier. We can change the intensity, make it brighter. No need to make it too bright, and we can change the focus so we end up with a nice sharp line. Now, when I've done that, I don't want to be on ground. I'm going to change this to DC because we're working on a DC circuit. Now, it's not measuring anything because we haven't connected it up. So what I'm going to now do, my black lead connects to my power supply back lead, and then my red lead, which is my signal, I'm going to connect to the output of my circuit. Now I don't need my LED in this circuit because, of course, we've already seen that it's flashing so quickly it just looks like it's staying on. So I'm going to remove the LED from the circuit, and I'm going to connect the output of my oscilloscope to where my LED went. And you should see a trace appear on the screen. Now that trace might be something like that or like that. You will have noticed that as I remove my output, it drops, put it in, it rises. But the output is flashing. In other words, it's going high, low, high, low, high, low. And we can see that happening here. Low, high, low, high. But that is happening really, really quickly. So I'm going to show you how to measure how quickly that is happening. So the best thing to do first of all is to change our time divisions. This is our time-based setting. And we want to change it so that when we look at our screen, we see a whole waveform, i.e. the amount of time it's on and the amount of time it's off. Now here we can't see that because we can't see the time it comes on here because it's off on the left. We can't see where it's off on the right either. So I'm going to change that, and now we can see one whole division. We can see where it's changed from low to high here, and we can see where it changes from low to high here. High to low, high to low. So looking at our sheet, what we want to do, we want to count the number of divisions for each on and off. In other words, one waveform. So I'm going to start counting from, and I can position this, I can move it along if I want to using the position button. So I'm going to move it so we start on a line, on a vertical line. There we go. So I'm starting there on this vertical line. I hope they're visible on the film. So 1, 2, 3, 4, 5. We have got 5 divisions there from where it starts to where it starts again. It wouldn't matter if we measured it at the bottom, from where it ends here to where it ends here. Okay, 1, 2, 3, 4, 5 divisions. So I'm going to write that into my table. So we have 5 divisions. Now, next is the time-based setting. So what was the time-based setting? If we look at this, our pointer is pointing at the number 1, but it is 1 millisecond, because these scales all differ: microseconds, milliseconds, seconds. So it's pointing at the 1 millisecond. So that is 1 millisecond. What is the measured time period? Well, the measured time period is number 1 times number 2. So this column times this column. So it is 5 times 1 millisecond. Well, we don't need a calculator for that because the answer must be 5 milliseconds. So what it's saying is it's taking 5 milliseconds to go on and off. Now, how fast is that? Well, 5 milliseconds is our time. But we want to know the frequency. In other words, how many times per second was that LED flashing on or off? So 5 milliseconds is 5 exponent minus 3. And we want to do x to the minus 1, which will tell us that it is frequency is 1 divided by time, and that x to the minus 1 button divides what we've put in there by 1, or sorry, 1 divided by that. And I press equals, and it tells me that the answer is 200. So it tells us that the time taken for one flash is 5 milliseconds, and that means it is flashing 200 times every second. No wonder we can't see it. The human eye can generally only see something flash, turn on and off, about 20 times every second at the most. Okay, let's move on to the next one, a 1 kilo ohm and a 1 microfarad. So I'm going to change the 2.2K. In fact, as I do this, let's look at the oscilloscope trace. So now that's gone just high all the time. I'm going to put that into there. And there we go. Now you can see on my oscilloscope trace, I've got a lot more divisions on the screen. Now that must mean that it's flashing a lot quicker. I've changed the value of the resistor for a smaller one, and now I've got far more divisions. It's more compressed. So what I'm going to do, I'm going to change my time base. So that there's a little trigger button there as well, which will just settle things. So there is my trace. I'm going to change it so I'm starting on a vertical line. And how many divisions is one waveform? Starting at the top there, 1, 2, 3, 4, about 4.8 divisions. There are little scales on here that probably aren't obvious on the video. So 4.8 divisions, let's enter that in. And what is the time base setting? Our time base now has changed because we compressed the values. So 0.5 milliseconds. 0.5 milliseconds. Now that is a slightly more difficult calculation to do than 5 times 1 here. So now we've got 4.8 divisions times 0.5 exponent minus 3, and that will give us 2.4 times 10 to the minus 3. Now that is milliseconds. To the minus 3 is milliseconds. So the answer is 2.4 milliseconds. Let me just move that a little. Right, so what it's now telling us, we reduce the value of the resistor, and now the time period has pretty much halved, hasn't it? What frequency is that? Well, we can work that out on a calculator, because frequency is equal to 1 divided by time. So there's our time. So if we press the x to the minus 1 button, which is like doing 1 divided by that answer, it equals 416.6. I'm just going to write in 416. Next, 4.7K and 0.1 microfarads. So this is where my little blue capacitor comes in. And a 4.7K. So I put that in again. Let's change that so we can just see the right number of divisions. And here we go, sorry, probably better to do that way. Starting there, at the beginning of the top line, 1, 2, 3, 4, 5.2. 5.2 divisions. And the time base setting now is set at 0.2 milliseconds. 0.2 milliseconds. So in our calculator, we have 5.2 times 0.2 exponent minus 3 equals 1.04 times 10 to the minus 3, 1.04 milliseconds. 1.04 milliseconds. Just leave it in your calculator. Now we want to work out that frequency, what it is as a frequency, if that's the amount of time it takes. X to the minus 1 equals 961. 961. Last one, 2.2K and 0.1 microfarads. So I just need to remove that resistor, go back to my original resistor, and looking at the screen, there we go again. Let's change that to, so we can see one waveform, place it at the beginning of a line, starting there, 1, 2, 3, 4, 5.2 divisions. 5.2 divisions. The time base setting here is now at 0.1 milliseconds. 0.1 milliseconds. So once again, 5.2 times 0.1 exponent minus 3 equals. Now you will see on the calculator it is put it at 5.2 times 10 to the minus 4. Now that minus 4 is not a number we use in standard form, but we have a really good button on here called the engineering button. If I press this, it will put it back into standard form. So I'm just going to press, bang, 520 times 10 to the minus 6. That's the same as 520 microseconds. But we've been working in milliseconds here, and I quite like it to go into that form. So if I press Shift Engineering, watch what happens. It puts it into standard form, but the next standard form up. So it's now saying 0.52 milliseconds. That is the same as 520 microseconds. Shift Engineering, milliseconds, engineering, microseconds. So 0.52 milliseconds. X to the minus 1 equals a frequency of 1923. 1923. Now I should say that the unit of frequency is the hertz. So what we're saying is, on the first one it was flashing at a rate of 200 hertz, 200 times a second. The second one 416 times a second, down to the last one where it was flashing at 1923 times every second. Now we would never have seen that on an LED, but we can see that on our oscilloscope. Okay, let's have a look at the calculation that we do with this, so that we can check whether our circuit is accurate with what it should have been given those values. It's the same as we did in the previous tutorial. 2 times C, which is 1 microfarad, 1 exponent minus 6, times 2.2K, 2.2 exponent 3, equals, and that is our time. So that was 4.4 microseconds. Sorry, 4.4 milliseconds. And then x to the minus 1 gives us a frequency 227. That was what we measured it to be. This is what we've calculated it to be. 2 times 1 exponent 3 times 1 exponent minus 6 equals, that's 2 milliseconds. and the frequency x to the minus 1 equals 500. 2.4, 416, 2 and 500. Thirdly, 2 times 4.7 exponent 3 times 0.1 exponent minus 6 equals, now once again this is put it to the minus 4, we don't want that, put it engineering, we don't really want it in microseconds, shift engineering gives us 0.94 milliseconds, x to the minus 1 equals 1063. So 1.04, 0.94, 961, 1063. And the final calculation, 2 times 2.2 exponent 3 times 0.1 exponent minus 6 equals, shift engineering will put it to milli 0.44 milliseconds, x to the minus 1 equals 2272 hertz. So, a relaxation oscillator, where we measure the output using an oscilloscope. Some good calculations in there using our calculator and engineering buttons and standard form. Are the results accurate? Well, we can look at either the measured time periods or the measured frequencies. Doesn't really matter. Let's compare frequencies because they're larger numbers. 200, 227, 416, 500, 961, 1063, 1923, 2272. They're all just a little bit below what they should have been, but they are relatively close. Of course, what we do have is a lot of tolerance, both in the resistor values and more importantly in the capacitor values, because capacitors are notoriously inaccurate. They can have tolerances of up to 50%. But otherwise, that's quite a good experiment, and hopefully has introduced you to using oscilloscopes. This is the end of tutorial 11.